It's great to be here. Perimeter Institute had me to give this lecture to a popular lecture last night. But of course, the reason I'm really here is to find out what's going on here, because this is like the epicenter of quantum information processing and quantum computing in the world. And so I am really here to learn about stuff. I also need to apologize to Olaf Dreyer. Last night when I said that the birds are quick to escape Hamburg in the wintertime, I would like to point out that they're also just as quick to come back in the spring. Not merely for the good beer. Okay. All right. So I'd like to talk to you about the quantum mechanics of closed time-like curves. So, of course, this sounds pretty wacky, and it is wacky because it is the quantum mechanics of time travel, essentially. So in quantum mechanics, we're accustomed to the situation where our intuitions don't work out to be true, and when you add in time travel, your intuitions doubly don't work out to be true. Now, this may sound kind of wacky and science fiction-y, and in fact, if you look at the history of time travel, there's a long literature about the history of time and about time travel. Interestingly, for most of it, you go into the distant past, it's most about time travel to the future, which actually isn't that hard because we're doing that right now. So in the Mahabharata, there's a great scene where this king goes to visit Brahma in his beautiful palace, and he's there for a few days partying like mad. And when he comes back, countless eons have passed and his entire civilization has decayed into dust. And there's a beautiful Japanese story called Urashima Taro, where a fisherman, Urashima Taro, frees a sea turtle from a net. And then a few days later, a very beautiful turtle princess comes and invites him to the house of the Sea King, and he takes her invitation, and they're married, and it's a great time, and he lives there in great splendor for 3 years. But he misses his parents, and so he begs her to let him go back. And so she says, okay, you can go back, and I'm going to give you this box covered with beautiful seashells, but you must not open the box. You can already see where this is going. And so Urashima Taro comes back. He lands on the beach of his island. Everything looks strange. He goes to his village. His village is no longer there. He finally finds this monument to his parents and to himself saying that he died 300 years ago. So in despair, he says, well, gosh, maybe if I open the box, I'll be able to see them again. So he opens the box, and this mist comes out and envelops him, and he feels himself rapidly turning into a very old man, and then he dies. All right. This is there's another an Irish legend about Finn McCool, the famous Irish hero, who goes to visit the king of the fairies and stays there for a few days partying like mad, which if you've read the legends of Finn McCool, you know he could really party like mad. And he comes back, and when he goes away, the king of the fairies gives him a magic horse, which he rides back on, and he tells him, whatever you do, don't get off the horse. So what does he do? Of course, he gets off the horse, just like Urashima Taro. You get, it's like whenever they give you some magic talisman and tell you not to do something, they always do it. So he gets off the horse, and as soon as his foot touches the ground, then he turns into an old man and dies. Right? We detect a pattern here in these stories. So the first stories about travel into the past, so time travel into the past, show up in the 1700s, but they don't really kind of get the notion of time travel, and it's not really until there's also Mark Twain's famous story, A Connecticut Yankee in King Arthur's Court, in which this Connecticut engineer he's hit on the head on the job site, and he ends up in King Arthur's Court, where he decides to modernize things and hence wreaks total havoc, destroys the civilization, etc., which is, kind of a metaphor for modern times, too. But it's not really until H.G. Wells' famous story, The Time Machine, that we actually see the kind of picture of time travel which we're familiar with from movies and books today. In that famous story, there's a machine which the time traveler enters, and it allows him or her to go backwards in time to a specific date and then come back to the future, and or back to the present. Now, once these stories got started about real time travel, people really began to think of the contradictions inherent in time travel. And there are really actually, so you got to be careful in thinking about time travel because, there are a number of paradoxes which I'll describe, and I'll describe how our theory, and I should say our experiment as well, because with Ephraim Steinberg we did an experiment I'll describe to you, effectively sending a photon a few billionths of a second backwards in time. And what do you do if you send what's the first thing you would think of trying to do if you have the photon interacting with its past self? What would you have it try to do? Would you have it buy its former self a beer, which would be the nice thing to do? No, of course, we have it try to kill itself. So we have it try to go backwards in time and kill its former self, and then we see what happens. I'll give you a hint. You know those movies where they say at the end, no animals were harmed in the filming of this movie? Well, that would be, to say that no photons were harmed in the course of this experiment would be an exaggeration. Okay, so the notion, so in time travel stories, there are basically two types. There are two fundamental paradoxes about time travel. And one is the so-called grandfather paradox, where the time traveler goes back in time and either inadvertently or on purpose kills her grandfather before he meets her grandmother. So she doesn't exist, so she can't go backwards in time. So what the hell is that about? How does that work? There are essentially two resolutions of this paradox. One is that when she does this, she can kill her grandfather, and in doing so, she enters an alternate world. So there's this famous, I think is it a Ray Bradbury story where called The Sound of Distant Thunder, where the time traveler goes back to like the Jurassic period and determined not to change anything, but he inadvertently steps on a butterfly. And because of the famous butterfly effect, when he returns to the present, everything is weird. Like it's sort of like it was, but the politicians are different, and like the language is spelled in a different fashion, etc. So that's one version in which you enter into an alternative universe when you come back to the present. And the other is that you can't do anything that's inconsistent with the past. So if you look at movies about this, so for instance, the movie Back to the Future, not to mention the famous movie Back to the Future, not to mention the slightly less famous movie Hot Tub Time Machine, which I haven't seen, but I have had it described to me, is of the type where you go back, you come back to the future, when you go back into the past, you change the past and you enter an alternative future. The other type, which is exemplified by the movie Harry and the book Harry Potter and the Prisoner of Azkaban. Who here has seen this movie? Okay, great. All right, I'm glad some people have. Don't you guys ever get out? I know we're a little far from town here, but come on. So in that movie, Harry and his wizarding buddies are doing all this stuff, and all kinds of weird crap is happening, and they can't figure out what the heck is going on. But in the end, they figure out that what's happening is that they've been interacting with themselves coming backwards in time, but everything is self-consistent. So things are weird and strange, but they're self-consistent. So for the grandfather paradox, this would correspond to a situation in which the time traveler is unable to kill her grandfather no matter what she does. I'm sorry, I'm going to use you for this example since you're sitting in the front row. So she points the gun at her grandfather and blam, pulls the trigger, and whoop, at the last minute, a quantum fluctuation whisks the bullet out of the way. So there are two, the prevailing theory of closed time-like curves is due to David Deutsch. Quantum mechanics of closed time-like curves is due to David Deutsch. This is a theory of the first kind, where you can enter into an alternative universe. And the one that I'm going to tell you about, projective closed time-like curves, is of the second kind, where you cannot actually go back and kill your grandfather. Okay? All right. So, are there any questions at this point? Any more time travel stories you want me to hear about? I've been collecting time travel movies. And any good time travel movies you want me to go and watch? Sorry.
I just have a question.
Yeah.
How would you know you've traveled back in time if you can't interact?
If you can't what?
You can't
No, you can interact. You can interact, but you cannot cause something to happen which you know not to be the case. Right? So obviously this is someone who's not seen Prisoner of Azkaban. So what's your problem? Right? Yeah. So you can interact with the past and make all kinds of weird things happen, and in the future you'll remember that those weird things happen. So you can certainly interact with things, but you can't go and actually change the past. So you can't go back and that horrible blind date that you had when you were like 15. You can't go back and undo that. I'm sorry. So, yes.
Primer.
Primer.
Primer. That's the time travel movie.
Yeah. I've heard that this is a really awesome movie. Who here has seen Primer? Yeah. I've heard this is really awesome. This is definitely on my list of things. And there's this one like 8 monkeys or 10 monkeys? 12 monkeys. 12 monkeys. 12 monkeys. I'm told with one slight mishap is of the second kind, where you go back in time, the time traveler goes back in time, tries to change some horrible thing happening, and it doesn't happen. I've heard it's an awesome movie, too. Yeah?
Seen Time Traveler's Wife?
Oh, the book, The Time Traveler's Wife. I started reading that, and maybe because I'm too close to the subject, I had to stop after like 50 pages. So, what is that? Which category does that?
Movies like Azkaban, it's very good, but it asks, the grandfather paradoxes, can you go back in time and kill your grandfather? This asks, can you go back in time and modify your most intimate relationships?
Right. Yeah. Well,
I thought it was a very good movie.
Excellent. So that actually sounds like. Is this possible to modify your most intimate relationship? Oh, gotta go see the movie. Okay. All right. Yeah.
So I've seen this one, but Charlie told me one in Futurama.
Futurama. Yeah. See, the problem is there's so many of these things that I can't see them all. But yeah, so? Which type does this fall under?
Basically, it's again about the grandfather paradox again. He managed to kill his grandfather.
He did manage. Okay. There you go. Awesome. Okay, so this brings up another one. Yeah, I always say that if I went back in the time and met my grandfather, I really was very fond of my grandfather, I would certainly buy him a beer. And only if we had too many beers and got in a fight would I accidentally kill him. Yeah, so there's another famous story about the grandfather paradox in which the time traveler goes back in time, goes to a club, meets a beautiful woman, sleeps with her. They do not practice safe sex, which I do not recommend. And then she gets pregnant, and it turns she gives birth to his mother. So he is his own grandfather. All right, that's another grandfather paradox. This actually, thank you for bringing that up. So this is the second major paradox about time travel. Let me explain it in less kind of, since I talked about quantum hanky-panky last night, I'm uncomfortable being seen as the resident quantum pornographer. Hey, if you look at technologies, one of the main things that drives their introduction is pornography, right? So if we could come up with quantum pornography, that might be good. Pictures of naked electrons, well, never mind. So the second major paradox is what's called the unproved theorem paradox. So in this paradox, the time traveler reads a cool proof of a theorem in a book, and she goes back in time and she shows the proof to a mathematician, and the mathematician says, wow, what a cool proof, I'm going to include it in my book. And the book, of course, is the same book in which she obtained the proof in the first place. And now you have something that's, this is actually quite disturbing because you have a carefully constructed, beautiful proof that came from nowhere. It was never produced. And actually, this other version of the grandfather story is, in fact, the unproved theorem paradox in disguise, because if you go back and become your own grandfather, then a quarter of your DNA came from nowhere, right? It was never subjected to natural selection or anything like that. So, in fact, the problem there is this unproved theorem paradox. I'm trying to do a lot of research on the kind of like philosophy and things of time travel. I haven't been able to find time travel paradoxes, which are not variations on these two themes. So any theory of time travel in quantum mechanics or elsewhere has got to come up with a resolution of these paradoxes. And so I will tell you what our resolutions of those paradoxes are. But first, let me give a little bit of history. So the fact, we probably wouldn't be discussing this at all if Kurt Gödel in 1948 hadn't, Gödel, when he was a famous logician, and when he got to the Institute of Advanced Study, he thought Einstein was there, and Gödel and Einstein were buddies, so Gödel learned general relativity. And Gödel, because he was fond of paradoxes, he decided that he would say, wow, maybe it's possible to have a space-time that has closed time-like curves in it. So, it's just as you have this funny space-time manifold, and it could be possible that you have a path that goes backwards and you end up in the past. And the way that this normally looks is a famous coffee cup picture. So time goes up here. We have this is in a 1 + 1 dimensional space-time space. So it looks down here, space is just like some big circle. And then here's the handle of the coffee cup, and time is flowing here, over here. But down here, if you go around this handle, time goes like that, and you can end up interacting with yourself in the past. Okay? So actually, the Gödel spacetimes are really weird looking. They're these big clouds massive clouds of swirling dust. It seems to be important to have rotation in these spacetimes to have closed time-like curves, but they do indeed have closed time-like curves. This is what's called a time-like wormhole. So, and lest you think that this is just some weird, wacky thing, and by the way, Google Images has some great pictures of Gödel spacetimes. I've been told that Gödel, when he told Einstein about this, it was sort of like a birthday present for Einstein, and Einstein hated it. Einstein was not Mr. Paradox guy. He didn't like quantum mechanics and like paradoxes. Everything was supposed to be cut and dried, but not so Gödel. But it's also a fact so that basically when you take any space-time and it's rotating sufficiently, and there's sufficient amount of mass, you'll get a closed time-like curve. So the interior of a Kerr black hole, a rotating black hole, inevitably has closed time-like curves in it. Back me up, Olaf, or some other gravitational person here. I mean, this is actually a fact. And unless you think that's like who cares about what happens inside a Kerr black hole? If our space-time itself, if our universe is actually overdense and so it's collapsing, then it is effectively a black hole. And if there's even a tiny bit of net rotation of the whole universe, then there would be closed time-like curves within our universe. So, it's not... General relativity allows closed time-like curves, and you could say in some circumstances it even encourages them to happen. So how do you deal with this? Well, there's so how in particular do you deal with things like the second law of thermodynamics going around here? What's the quantum structure of the quantum states? Can you even have a quantum Hilbert space picture of what's going on inside this closed time-like curve? The answer to that actually is you can have a quantum Hilbert space picture, but you cannot assign a quantum state, just to give away, telegraph some of the punches. So the next hint of how you might deal with quantum mechanics of closed time-like curves comes from John Wheeler. This is not anything he published. Amusingly, this is reported by Feynman in his Nobel Prize acceptance speech, which is online, so you can get it. And you go look at it, and there's this place where he starts off with kind of this dry stuff, but then he starts talking about his experience. And there's this place where he says, I'm going to try to paraphrase it in a Feynman-esque kind of way. He says, well, Johnny Wheeler called me up from the Institute, and he said, I know why all electrons have the same mass. And Feynman said, really? And Wheeler then said, yes, and I also know why they have the same mass as the positron. And Feynman said, why? And Wheeler said, well, time, by the way, time is always going to go up in this picture because anything to do with general relativity has time going up, okay? So get used to it. So Wheeler says, well, look, electrons and positrons are always created in pairs, E plus, E minus. And they're always destroyed in pairs. E minus, E plus. So we can think that what's going on is that there's just one electron that's going forward and backward in time, and that when it's going forward in time and it's an electron, and when it gets destroyed, it turns around and becomes a positron. So the reason that they all have the same mass is there's only one of them. And the reason why they have opposite charge but identical charge is that when you do charge or time reversal, you take plus charge to minus charge by a famous theorem of quantum field theory, the CPT theorem. So, and Feynman said, then he says, this was totally crazy, but I did steal from this the notion that positrons are electrons going backwards in time. So in fact, at the heart of contemporary quantum field theory, with the notion that positrons are electrons going backwards in time, there's this crazy idea of Wheeler's that says, look, there's only one electron and one positron. And of course, if you went and go look at Feynman diagrams, you realize why this isn't really true, because of course you can have other Feynman diagrams that are like this, and they're connected by photons. And so there's probably not only one electron and one in the universe. Though it is a kind of a nice idea if there's only one electron. Okay. So you can think, so what I'm going to tell you right now is that what I'm going to tell you, our theory, which is with Lorenzo Maccone, Yutaka Shikano, Raul Garcia Perez Patron, and then also we have Ephraim Steinberg's experimental group at University of Toronto did the experiment. What I'm going to tell you, you can think of as essentially the mathematization of this Wheeler notion of positrons being electrons going backwards in time. And it's going to rely strictly on entanglement. And indeed, when you create electrons and positrons in pairs out of the vacuum, their spins are in entanglet singlet states. And when you destroy them, the only place they can be destroyed is in entanglet singlet states. And this is going to be key for how this theory of time travel works. But let me continue with the theory a little bit, because I think it's important to know about. I have this master's degree in history and philosophy of science from Cambridge, so I actually think that theory, the history of ideas, is actually quite important to understanding what the next idea is going to come from. Okay, so around on 1988, Kip Thorne and Uri Yurtsever, and then later in the early 1990s, Jim Hartle and David Politzer looked at path integral approaches. So path integrals, of course, what you do is you take a bunch of classical trajectories and you assign them an action and you sum e to the is over all classical trajectories. And what they did is they say we only take classical trajectories, classical paths, which are self-consistent. Right, so we just assign classical. In classical mechanics, you don't have this many worlds stuff that David Deutsch advocated, but we're only going to take these classical paths that are self-consistent, so we sum over self-consistent classical paths. And this is actually a perfectly reasonable idea, and you can formulate it. The problem is that path integrals are very hard to evaluate, so they never got very far with this approach. But they were able to look at it. And then David Deutsch in 1990 came up with this. And maybe I should actually start. Yeah, this is the right order. So in 1990, no, this is not the right order. Yeah, that's the right order. Okay, fine. David, it's not the right order. So I want to especially mention that Charlie Bennett and Ben Schumacher, Charlie Bennett in particular, starting with the invention of teleportation, which was, when was teleportation? It was around, do you remember, Debbie? 94? 92, yeah. So starting with teleportation, Charlie Bennett talked about, with teleportation, you have, I'll be kind of graphically suggestive about this. You have an entangled singlet, and then you make a measurement right here, and then you send classical information over here. You perform some operation dependent on this classical information. This is a Bell measurement. And then you do something right here, and if you have a state psi, you end up getting the state psi here. And Charlie Bennett always talked about teleportation as if this part, where did the information go, as if the quantum information went here, and this is the quantum information going backwards in time and forwards again. So, and this, by the way, this idea is at the essence of what I'm going to tell you about. So, unfortunately, this is kind of unfortunately, Bennett and Schumacher have never published anything on this. They've talked about it for years. They never really developed, so far as I can tell, any explicit theory about this. So you could also say that what we're doing is really developing a theory out of this. Really, it was a metaphorical description that Charlie Bennett has been using for decades now. Okay, so now let's get down to, and this is all history, and now it's going to be like math and stuff like that. So are there any more historical questions or comments or things like that? Were you bored by hearing the history of this? Maybe you were. That's okay. Okay. I'm sorry?
Which paradox does arbitrage come in?
Arbitrage?
Yeah, so why didn't he send
So that could be, so that's consistent with both, so this is like a many worlds version. So enter another world, let's call this is enter another world. And this is same self-consistent world. So if you send information about what the price of the Swiss franc is going to be back in time and then invest in the Swiss franc, well, as long as the amount of your investment is sufficiently small that the history of the Swiss franc is the same, then it's okay. But if you try to buy all the Swiss francs, then it will cause things to go haywire, and so then it would fall in this many worlds version. So you can imagine making money off of time travel in either of these worlds. In this way, you can make a lot more money in this world, in the Deutsche version, the many world version. Yeah. Okay. Okay, so enough of this fun fooling around with history, fooling around with the past, which is, of course, what time travel is about. Let me now actually tell you how these things work. And the first thing I'd like to tell you is about David Deutsch's theory. So I'm going to review, who here is familiar with Deutsch's theory of closed timeline curves? Yeah, some people are. So let me just tell you how Deutsch, I'll switch colors for blue for serious stuff. So this Deutsch, let me describe to you what this Deutsch paper in 1990 does. It's, by the way, even though we think our theory of time travel is better, for reasons I'll tell you, this is a beautiful and elegant theory because it's very hard to formulate quantum mechanics in these contexts. These path integral approaches are a good start, but it's tough to deal with these paradoxes. So let me tell you what Deutsch suggested and how he dealt with this paradox here. So Deutsch is, nope, I guess I won't use this one. I'll throw that one on the ground. And we'll use this one. Okay, so the way that Deutsch's theory works like this. You have kind of normal, what he called chronology respecting degrees of freedom. And let's call this is in the state rho A. And then you have the closed time-like curve. And this could be many degrees of freedom. I'm just going to do this if it's 2 qubits, but it could be many different degrees of freedom. And let's just call this, this is rho B. And you have some interaction between these things. And then the question is, how do you make sense of what happens up here? Now, interestingly, Deutsch does not tell you what happens over here. He does not assign this a degree of freedom, this thing going backwards in time. So it's sort of funny if you think of this coffee cup picture because there's something happening in the handle of the coffee cup. But Deutsch does not give you a state for this, which is already a hint that something is a little fishy. So Deutsch's self-consistency condition basically says that here we have rho prime of A, and here we have rho prime. Sorry, I should put it right here. So at this point right here, you have rho of AB. Now let's actually, yes. So, and this is, so when the thing comes out, let's call it rho prime of AB. When it goes in, it's in the state rho A tensor rho B. And then what he asks is that the state, the reduced density matrix for the system that comes out of this closed time-like curve is the state rho B. Right? You can see why this gives you a self-consistency condition because it says that the thing that enters the closed time, the state that enters the closed time-like curve in the future is the same as the state that emerges from the closed time-like curve in the past. So this condition is the trace over A, rho A, U rho A tensor rho B, U dagger is equal to rho B. Okay, this is Deutsch's self-consistency condition. All right. So you see how this. I mean, this makes sense, right? He wants this to be the states to be self-consistent, and he wants this state to be the same as the state there. Moreover, this is because this is a super operator. This is the same as saying if I have some super operator, which is this interact with row A via U and then just look at B. This is really a super. You're asking that the state row B be an eigenstate with eigenvalue 1 of this corresponding super operator to this process. And because super operators always have an eigenstate with eigenvalue 1, such states always exist. Okay? So it's a nice self-consistency condition. It looks good. Okay. Now, so let's look at actually what happens then if we do something where, no, let me just leave it at that. Let me just mention some things that are a little disturbing about this before I go on and tell you. Well, I'll tell you our theory, and then I will compare the two of them. There is something a little disturbing here, okay? So Deutsch is assuming, if you look at it, he's actually assuming that when the time traveler exits from the curve, and there's another, the rest of the universe is out there, that they are in this tensor product state. Which means that the time traveler, when she exits from the curve, is completely uncorrelated with the stuff outside of the curve. That is, she emerges in a universe where none of her memories are any good. They don't correspond to the universe she sees. That's a little disturbing already, because that's certainly not, that's not this Urashima Taro kind of time travel or H.G. Wells kind of time travel. It's like you end up in this weird place that has nothing whatsoever to do with what you remember. And the reason for this, of course, is that so I would describe this in quantum information terms as that I personally would prefer a closed time-like curve to behave like a quantum channel. And quantum channels preserve correlations with the surroundings. But by demanding only that the reduced density matrix be the same as it enters the curve in the future and emerges in the past, in this case, you're actually erasing all memories of outside. So this is not behaving like a quantum channel. So this is a bit disturbing. I should say that after we wrote our paper, we corresponded with Deutsch about this, and he said that he found aspects of his theory unsatisfactory, and I believe that this might be one of those aspects that he found unsatisfactory. Yeah?
The result is the super operator linear?
Yeah, sure. This is like, so if I, any super operator can be written as a unitary interaction with an environment when you start off in the tensor product state. So it's just, this is a Huzy-Wutz's theorem. I don't know whose theorem it is. So the transformation that B undergoes when I take U, it interacts with A, and I take the trace over A. This is certainly a legitimate quantum mechanical transformation. It corresponds to a super operator. It is linear. Okay, and then. So this is a super operator, and all super operators have a eigenstate with eigenvalue 1. There is a nonlinearity in Deutsch's theory. So this transformation is linear. There is a nonlinearity because what Deutsch is saying is that the only row that we can allow are things that satisfy this. So you can't put anything in here. You can only put rows that satisfy this. So it's not anything can go through this closed time-like curve. So there's a nonlinearity in the sense that you're selecting out of the set of possible states just these rows of B from which it can happen. There may be multiple rows of B for which this is the case. That is, the eigenvalue may be degenerate. And in that case, for reasons that I'll describe in just a second, Deutsch says, take the one with maximum entropy. Actually, I'll describe it in a second. So the reason for that is that if you don't take the row sub B that has maximum entropy, then you immediately run into this unproved theorem paradox. Because the unproved theorem paradox you can have is perfectly self-consistent. You can have the unproved theorem go through this, everything is fine. And I mean, if you just think of this kind of some classical transformation, and then that's bad. Deutsch really doesn't like that. If you read his paper, which is a really excellent and interesting paper, he spends a lot of time talking about this unproved theorem paradox and how much he's upset by it. And now he says, okay, you take the maximum entropy one. All right. So Let me now contrast this with, any more questions about this? I'm going to stop talking about this Deutsch thing right now. There's more disturbing things, as we'll see in just a second, about this. Actually, I'll mention one more disturbing thing, which is that Scott Aaronson, John Watrous, and Todd Brennan and a bunch of other people have shown that this is absurdly computationally powerful. So this nonlinearity of selecting out the particular states allows you to solve anything in, so Deutsch CTCs allow you to solve anything in p-space in plus computation, both classical and quantum computation. It says that p-space is equal to polynomial time. So you can solve any problem in polynomial space, in polynomial time, and for you computational complexity people out there, and I know you're there because I see you, you know that anything that is this case is really bad. And if you say that you can do this, then computer scientists will immediately disbelieve that this is possible, all physical evidence aside. All right? So that's actually kind of a bad thing for this. And I should say that the way I got involved in this is that there was a paper from IBM in which summer before this last one, where they objected to this Aaronson result. And is anybody co-author of the paper here in this room right now? I just want to, because I want you to step up and defend it if you are. Anyway, so this caused a big argument, and this was what got us. We found this argument to be annoying, so we decided to work on these closed timeline curves ourselves. And when Charlie Bennett came, I'm sorry?
What annoys you about the argument?
What annoys me about the argument? Yeah, because I don't believe it. That's why I don't.
Is it the opposing idea, or you don't believe in the argument itself?
So the Aaronson paper is correct. I've went through it very carefully. The IBM argument says that in the presence of closed time-like curves, you cannot prepare your computer in a particular problem state in order to solve that problem. Now, I don't know if this argument is correct or not, but the two papers start from different assumptions. And I actually quite distrust the argument from the IBM paper. Anyway, we brought Charlie Bennett to MIT, and we put him and Scott Aaronson in the steel cage, and we had them duke it out. And it was inconclusive in the end. I would prefer not to discuss this paper because I don't think it's very illuminating. So I shouldn't have brought it up. OK. All right. So actually, when we looked at this, I said to myself, I actually know of another way of doing closed time-like curves. Because about 8 or 9 years ago, I worked on this problem of how information escapes from black holes. This, by the way, this talk has every wacky possible thing you can imagine. It's got closed time-like curves. We're going to have teleportation. That's like the least wacky of things. And we're going to have how information escapes from black holes. So let me review how this model works. So I said, there's something very funny about this, because there's another Aaronson paper which says that quantum computing plus post-selection is equivalent to solving the class of computational class probabilistic polynomial time, affectionately known as PP, which when I told my children that there was a computational complexity class known as PP, they thought that was really hysterical. So because my working on black hole, escaping from black holes, I happen to know that you can make a theory of closed time-like curves based on quantum mechanical post-selections, which I'll now present to you, which I thought all along was equivalent to Deutsch's theory. I should note that Charlie Bennett and Ben Schumacher, while they've been talking about this, going backwards in time in a method that's very close to what I'm going to describe, and they were also not aware that their theory was different from Deutsch's. Now, if you look at these two things together, so if you can get, with post-selection in quantum computing, you can get closed time-like curves, which I'll show you in just a second, then you've proved that PP equals P space, which would be really news to lots of people. You would have collapsed part of the polynomial hierarchy, which would be pretty amazing. So the first way we start on this is that we said, hey, look, we can prove that PP equals P space. Well, if you've ever worked on these things, you know that after a weekend of working on it, you realize that you were wrong. But it was fun for about a weekend, OK? And the resolution was that we realized that, in fact, the closed time-like curves via post-selection are not equivalent to Deutsch's closed time-like curves. So let me tell you how this works. So let's look at first at black hole, escape from a black hole. How does escape from a black hole work? Okay, so here again is time going up. Here's space. Here is my picture of a black hole. This is the horizon, the event horizon of the black hole. This is the singularity, where everything gets smushed into nothingness, okay? Note that the singularity of a black hole is space-like. It's not actually point-like, it's space-like, which is kind of interesting. Note also the horizon is light-like. Light goes at 45-degree angles here. You can see why the horizon is light-like, because if you're right at the horizon of a black hole, and you send off a beam of light that's just trying to escape from it, say at an angle, then this beam of light will just go rotating around the black hole. So if you want to take a path that hugs the horizon, it's a light-like path. So the horizon is a light-like surface. So here is the picture of what happens. We have this, this poor innocuous state falls into the black hole. It can be your favorite evil professor or something falling into the black hole. And it's going to get smushed at the horizon. But wait, there's more to this picture. Because outside of the horizon, Hawking radiation is being created. And the way that Hawking radiation works is that, let's do it like this, you have singlet pairs of particles are created from the vacuum. They're created in singlet states, because the only thing you can create something out of nothing is if it's in a singlet, because all conserved quantum numbers have to be 0. All right? They're created as singlets. Part of this vacuum fluctuation has negative energy and it falls into the black hole, thereby reducing its mass. And the other part is positive energy and it escapes to infinity, thereby carrying part of the mass of the black hole off to infinity, and that's how black holes evaporate. Okay, now there's a lot of debate about what happens about information in black holes, but there's one mechanism proposed by Gary Horowitz and Juan Maldacena, two heavyweight string theorist types. And the mechanism is the following. And I'm going to describe it in the way that makes it sound most plausible, even though nobody knows if this mechanism takes place or not. But let me just go with me for a second. So maybe it's the case that the only way, just in the same way it's only possible to create something from nothing is for it to be in a singlet state, maybe the only way you can have it go away to nothing, like at the singularity, is for it to be destroyed as a singlet state. So suppose that every state that falls in the black hole gets destroyed as a singlet or projected onto a singlet. Now let me be more explicit. Suppose that the singularity projects incoming stuff onto a singlet together with half of a Hawking radiation pair. All right? I mean, who knows, right? The great thing about being a theorist is that we have no idea what happens at the singularity. So let's just say it's whatever we want it to be, right? This is like experimentalists are not allowed this kind of leeway. All right. So now you can say, well, what is the state out here? Aha! We recognize that this is just like teleportation. Okay. Here's the singlet state right here. Here's the state psi. But here, we measure and get the singlet, which I will actually... Now, so we measure and get the singlet. And what that means, if you are familiar with teleportation, which I know lots of people are, in the singlet state is the one where Alice sends to Bob the information, whoa, don't do anything. You already have the state psi. And so I'll draw this like this, because now we have projection. This is creation of a singlet. This is projection onto a singlet. And so here's this nice picture, which this is the kind of thing that Charlie Bennett was fond of drawing. You know, that, oh, look, the information goes back here and then up here and out here, right here. All right? So is everybody okay with this? So in this case, if you project onto a singlet, which is a non-linear operation, right? It's like saying we make a Bell state measurement and we toss out the things that all 3/4 of it and we renormalize the get this. So the renormalization of the probability to 1 is nonlinear. And so this is nonlinear quantum mechanics, which is dangerous. That's how you can solve these hard problems using it. But at any rate, the state escapes from the black hole. Okay? Are people happy with this? Yeah?
But wouldn't we need to know the relative measurement?
Right. So in ordinary teleportation, you need ordinary teleportation. Everybody can do that. People have been doing this for decades. It's like anybody can do that. And you make a measurement, Bell state measurement. Actually, making the Bell state measurement, all the Bell state measurement is not so it's hard. But you make the Bell state measurement. You get 2 bits of information. Alice sends those 2 bits to Bob, and then Bob does something as a function of those bits. So the idea here is that a nonlinear process takes place, whereas instead of having an ordinary quantum measurement, it, for whatever reason, like you're at the singularity of a black hole, it projects you onto the singlet part. So it only gives you the singlet part. All the other stuff gets tossed away and now has probability 0. So
The ones make it out which were projected.
right, so only the ones make it out where this is projected on the singlet. This is totally illegal in ordinary quantum mechanics, so that's a very good question. This is not, it's illegal, so this is something nonlinear and bad. And you can see it's bad because already you have things that are propagating faster than the speed of light. You clearly have violated the no cloning theorem because, of course, this could be back down here, right? So you're definitely doing bad things. Yeah?
Well, you partly addressed my question, but what's unanswered here is what determines the physics of when it goes back into the future from the outside.
So that of course, interestingly, the back into the future part is the back to the future part. Like, and I note that one of the main actors in that is named Christopher Lloyd. No relation, I believe, only a distant relation. So interestingly, this part down here is really the kind of uncontroversial part. That's just entanglement. It's just an entangled singlet state. The controversial part, of course, is this projection part.
Well, sure, but I mean, it could go at any one of those times, including earlier in the past.
Yeah. Well, of course, right? Because let me segue, of course, because I realize that in indulging myself and telling you about history and talking about time travel movies and stuff like that, I'm going to run short on time. So as everybody knows, and by the way, I've noticed this. I try this out on just people I meet on the street who have nothing to do with physics, and they know this. So as everybody knows, if you can go faster than the speed of light, you can go backwards in time. Right? Everybody knows this. It's just like, that's the way it is. So, so here is the model for post-selected or projective closed time-like curves. So we create a singlet down here. We project. So this is create singlet. We project onto a singlet up here. And we renormalize probabilities, right? We normalize probs to 1. This is all really easy to do and calculate, right? Because it's just as if you were taking a measurement, a Bell state measurement, and you say, what's the conditional probability of everything else given that I got a singlet? So all probabilities in this theory are calculated using the conditional probabilities that you got a singlet here. All right, and then so here's this other thing, and then you have some transformation, and then something else comes out at the end. Okay. So probabilities of events. Equals conditional probabilities. So it's a very well-defined theory. The one thing that you have to say is, well, what if the probability of this is 0? And the answer then is, well, nothing, that can't happen. So, because conditional probabilities are not defined if the probability of the outcome is 0. So this just doesn't happen. Which is good, because now you can see already that we are going to always have things that are self-consistent. Because in this picture of closed time-like curves, what happens is a valid conditional probability for a sequence of events in quantum mechanics. It might be hugely improbable if you don't do the projection on a singlet, but it's still possible. So you can't get things that are exactly impossible, like, for instance, killing your grandfather. Okay. So now this is, so once you have this, and I want to again give Charlie Bennett and Ben Schumacher credit, even though I've actually had a rather annoying time dealing with them over this, because they have talked about things like this for a long time. I know that Raymond told me, I didn't know about this paper, that you guys did an experiment here with an NMR to look at this notion of like, oh, look, things are going backwards in time, let's look what happens with this. And I want to give them credit for talking about this for years, but I'm not going to give them credit for, I wish to express my annoyance at them for not writing this up as a paper so that we can actually see what they mean, because they never wrote it up. It only exists in the form of like 4 transparencies on a talk of Charlie Bennett. So they have a theory which is like this, but it's not clear what they meant by it. In fact, when we talk to them, they actually use quite a different language, and I'm not sure if we agree on stuff. At any rate, Charlie told me that they were unaware that their theory was different from Deutsch's, and this theory is definitely different from Deutsch's, as I'll now show you. And I'll show you by giving you a picture of a quantum circuit for our grandfather paradox experiment, and I'll show you that Deutsch's theory and our theory give different results for what happens. So, I can show this over here, so let's do a grandfather paradox. The simplest version of a grandfather paradox is something like this. Here's our closed time-like curve, okay? So 0 equals dead, 1 equals alive, and we're just going to switch this over to having our photon killing itself, right? So if you do a sigma x, you flip this around the x-axis right here, then what happens is 0 equals dead, 1 is equal to alive. And you see if you're alive here, you're dead here. You get turned into dead. If you're dead here, you get turned into alive here. So this is the grandfather paradox, the very simplest thing that you can imagine about it. And moreover, we're going to actually, in our experiment, we're going to ask this qubit to declare whether it's dead or alive. So here we're going to measure up here. So here we measure it, we couple it to 2 other qubits via controlled knot. And then we're going to ask it to declare if it's dead or alive. By the way, I think if you look at the grandfather paradox in Charlie Bennett's notes, again, trying to like decipher what they meant by this, it's a different paradox, and this might be why they didn't figure out that their result was different from Deutsch's. We also asked Charlie Bennett to be a co-author on our paper after we'd done the experiment and discovered that they'd been doing this before. And after this delayed the publication of the paper, the submission of the paper by 4 months, while he decided in the end that he hadn't contributed enough to it. So, sorry, I shouldn't express, but I shouldn't, this is like all, like, but hey, around here, it's like I might as well express, like, this is the kind of thing that happens in science, what the hey. You know, you got to negotiate with people get upset if you don't give them credit, etc. So I'm trying very hard to express, like, to give them credit and express my annoyance. Okay. Okay, so what happens here? All right, well, in Deutsch, this is totally okay, right? Remember, Deutsch always works. It always gives you something. So what is the state that will work here? What is a state where if I pop it in here, it comes around here, and it's still the same state?
Hadamard state.
I'm sorry?
A Hadamard state, equal superposition of 0 and 1.
Right, that's right. That will work. That will work, yeah. However, Deutsch asks us to take the maximum entropy state.
So a mixture then.
Right, so here, so the Deutsch, basically, I'll call this rho b again, rho b is equal to 1/2 0 0 plus 1 1. Actually, you see right now, since this was very alert, also, you know, we could also just have a state, a sigma x state. That would also be fine because it's an eigenstate of sigma x, right? This shows you why Deutsch has to say give you the maximum entropy state right here, because there's several states. Sigma, the minus 1 would also work. Okay, there are several states that have this criteria, and this state right here is like the unproved, the never created proof of the theorem. Right? It's a special state. Sigma x up, it went around, everything is totally fine, it's self-consistent, but it's some special state and nobody ever picked out why it should be sigma x, well, why it should be spin x up. So Deutsch says, okay, we got to use this state to make it fully mixed so that we don't run into this unproved theorem paradox. So, but now you see something truly strange and alarming here, which is that even though the density matrix for the state, the time traveler, as she enters into the future, the closed time-like curve in the future is the same as the density matrix in the past. Somehow, during the transition around this curve, the actual state has been mixed up. So 0 has become 1 and 1 has become 0. So this is a bad closed time-like curve to enter alive because you're dead when you exit. Of course, it's a good one if you're dead because you exit alive, right? I mean, so we could have both destruction of life and we could have creation of life from nothing from this. So that's pretty weird. So Deutsch's criterion, which looks perfectly fine to begin with, is actually, now you see when you apply it to this grandfather paradox, you say, hey, hold it now. I thought you said the state was the same. And the answer is the density matrix is the same, but your particular part of the density matrix may have gotten completely screwed up, which is bad if you were alive when you entered the curve. Okay.
Sorry.
Yeah.
What happens if you think the density matrix is a lack of knowledge? It's actually a pure state for someone.
Right. So of course, this also, as you can tell, when you have this kind of system, all your intuitions about quantum mechanics and what you've been taught, you've got to be careful about. Yeah. So if you think of it as a lack of knowledge from an outside observer, the outside observer, like the person out here monitoring the situation from over here, will say, well, I don't know what it was. Hold it. Let me go look over here. And they'll get statistics up here. And what they'll find is basically, in Deutsch's case, you get, if this one is 0, the next one is 1. If this one is 1, the next one is 0. So what it says, well, I didn't know if it was alive or dead when she was alive or dead when she went in, but by gum, whatever she was, if she was alive, she turned out dead, and if she was dead, she turned out alive. So I think it's still consistent, okay with that. So I think, yeah, it's, you didn't know beforehand, and then you found out. Yeah?
I think to use the Deutsch recipe for this problem, you should include the C knots as a part of your unitary.
Yeah, it is. Yeah. I didn't derive to you that this was the maximum entropy state from this, but I will actually, in fact, if you look at this, include it with the C naughts, take the trace over the C naught gates, you'll find that this state, the fully mixed state, satisfies Deutsch's self-consistency criterion, and because it's pretty clearly the maximum entropy state, unless you want to disagree with that too, then this is the Deutsch prediction. So if you have the C naughts, yeah, sorry about that. So if I have this, then it's okay. You're right. I'm sorry. You're right. I'm sorry. I didn't mean. I was unfairly scoffing at you. You're exactly right. If you put this in here, then this state doesn't work if you're actually doing these measurement interactions. Completely correct. Okay. So what happened with PCTCs? Well, what happens here is that this can never happen. If I think of it without the C naught, so let's to make your life easy, you see what happens is that the triplet right here, the singlet right here gets changed into a triplet, which has 0 overlap with the singlet, so that the projection onto the singlet is 0. Okay. So in just the raw grandfather paradox, it's an example where it doesn't happen. On the other hand, what happens? Let's suppose that you actually have something which is just e to the minus I theta sigma x. So you're performing a partial rotation around the x-axis. And e to the minus I theta sigma x is equal to cosine theta times the identity minus I sine theta sigma x. And what happens then is that this projection to triplet knocks out this. So in fact, the qubit never gets flipped. It only behaves like the identity. You just take the identity part, no matter how small it is, amplify it back up to 1. And so what PCTCs say is that you get 0, 0, 1, 1. If the time traveler entered the curve alive, she exits the curve alive. If she entered the curve dead, she exits the curve dead. And that's because these projective closed time-like curves behave like idealized quantum channels. They preserve not merely the state of the system when it enters a closed time-like curve, they also preserve any legitimate correlations with variables out here. So if you remember being alive when you enter the curve, or if somebody, maybe if your mother remembers that you were alive when they enter the curve, she will see you emerge alive in the past. Okay? So this already shows you that this Deutsch's closed time-like curves are different from these projective closed time-like curves, and the main difference is this quantum channel version. I'll also tell you, I'm out of time, but I will, let me just tell you what happens with the the second grandfather paradox, the unproved theorem paradox. So let me see if I can get this right. This is always it's always tricky. Here's the closed time-like curve. Okay, so what happens is this person, the time traveler, reads the theorem in the future. Okay, this is a qubit right here. Here's the theorem. Okay, and then in the past, she writes the theorem onto this qubit, right? So she tells the mathematician what the theorem is, and then she goes her merry way. So this is the unproved theorem paradox. And so let's say she needs to be able to read the qubit in the future, and then write it back in the past. And I claim this is the quantum version of this unproved theorem paradox. Sorry, I'm rushing through it a little bit, but so read theorem, and this is tell theorem. To read the theorem, she has to be in the state 0, so she knows what the theorem is, and then she tells it to the mathematician. This is a mathematician. This is the time traveler. So now you can ask, what happens here? What is the state right here? Now remember, when Deutsch does this circuit, what happens is he identifies this right here with this right here. But now any theorem will do. Could be 0, that's fine. 1 will do as well. So he has to take the maximum entropy state in order to get rid of this paradox. So basically Deutsch says, oh, okay, look, it's got to be the maximum entropy state up here. So you get a mixture of 0, 0 with 0, 0 and 1, 1 with 1, 1. And you see that Deutsch, by introducing this extra entropy in the problem, by having this maximum entropy state, he has randomized the theorem. So that's, so it's not some special proof or anything like that. However, you also see another problem or feature, let's say, it's not a bug, it's a feature of Deutsch's theory, which is that you're introducing entropy. You're taking pure states to mixed states. Whereas a moment's thought about this process will tell you that if this state is a pure state, then if you project out, and this state is a pure state, and you project out part of a pure state, then by gum, this state is a pure state. So PCTCs take pure states to pure states. Deutsch's takes pure states to mixtures. This is Deutsch. And what about PCTCs? Well, actually, people who have been doing quantum information for more than 6 or 7 years might recognize this as an entanglement swapping circuit. We create entanglement over here, and we swap the entanglement over here. So what we get right here is the pure state, which is 0, 0 plus 1, 1. And so now you see a neat feature, which is that we never even worried about this unproved theorem paradox until we formulated the theory. And then we looked at how the unproved theorem paradox plays out once you do the theory, and you find, look, the theorem is in a complete mixture. How did that happen? It's because entanglement stepped in to save the day and to prevent. It says, well, look, we have this pure state. Nothing here ever told the theorem to be one thing or another. We know that's a pure state, so it's got to be an entangled pure state with equal amplitudes for 0 and 1. So the theorem is just a pile of garbage. Okay, so let me just close by saying I need to thank Ephraim Steinberg and his colleagues. So we have a paper that describes this with the experiment. We did the experiment, right? So because you can do the experiment, because this is just like teleportation where you toss out 3/4 of the results. So anybody can do, well, not anybody, but lots of people can do teleportation experiments. So we can actually make this happen. We can't deterministically send information back into the past and mess with it, but we can do an experiment which, in a post-selected fashion, is completely equivalent. Now here's a place where I differ with Charlie and Ben. They call this a simulation of time travel. I would point out that this is, in some sense, a bit more. In fact, we're being very honest by saying, if you think of the initial teleportation experiments, they were all post-selected too. And if you actually calculate the fidelity of those experiments without post-selection, the fidelity is 0.111 or something like that. So when people like Zeilinger and DeMartini reported fidelities of 80%, 0.8 in their teleportation experiments, they're not. That doesn't mean that you could give them a qubit and have them teleport that qubit with fidelity 0.8. It means that in a post-selected fashion, when they post-select for the experiment succeeding, then they would teleport your qubit with fidelity of 0.8. So here I'm telling you right now, we're going to post-select it, and in a post-selected fashion, this is completely equivalent to sending things back in time. How does this work? You create the singlet, you create this other state, you create this time evolution. We actually have 4 qubits in this experiment. And then here, it's as if this measurement is like the photon entering the time machine. Right? Photon enters a time machine. If the red light goes on, which means you got a singlet state, then everything in the experiment, including all the measurements you did in the past, yield exactly the same results as if the photon had gone back in time and tried to mess with itself. Okay? So in a post-selected sense, this is time travel. It's, of course, not real time travel in the same sense that teleportation is not real teleportation. That's okay. I give them credit for them, and it's okay. I mean, here we should be more careful about talking about post-selection. So what were the results of the experiment? Well, it's actually very nice. So we find, indeed, that the photon never manages to kill itself in the past. The tool, they use a quantum dot source for a single photon quantum dot source, an entangled pair source. This is called a photon gun. That's its technical name, which is useful for us because I can describe them the following way. So what this means is that, like, when you take the photon gun and you point it off in that direction, let's do it off in that direction in case there's a mirror there, then the red light goes on a quarter of the time, and you never manage to kill yourself in the past. Now you take the photon gun and you start pointing it closer and closer. Let's say I, the photon, take the photon gun. I don't want to take advantage of you any longer, even though we managed to save you the last time around. I take the photon gun and point it closer and closer to my head in attempted photon self-suicide. Well, it's not really suicide. It's more like, I don't know what killing yourself in the past is like, but we attempt to kill myself in the past, and what happens is I still fail. When the red light goes on, I still fail, but now the red light, this is the probability of successful post-selection. The probability of the red light going on gets lower and lower until finally, so let's call it this angle, this is the angle phi. We start off at pi over 2, and we're going to end up at 0. And finally, when you get down to 0, the probability of successful post-selection goes to 0, because if with 100% probability I'm going to kill myself when going to the past, that's not okay. It violates logic, and so it doesn't happen. All right. So let me summarize. Oh, sorry. Okay, mine's the hockey. I've got mine is sharper. I just picked this up. It's like, Look, Ramon, as I told you tomorrow, I was going to go over. So, let me summarize. Closed time-like curves are a perfectly legitimate part of general relativity. Therefore, it's important to figure out what happens to them quantum mechanically. Now, they may not be allowed in our universe or not. We don't know. Stephen Hawking says no. He has this chronology protection postulate, which says you can't have closed time-like curves. On the other hand, since he doesn't give any reason for why this is so, it's like many of his other statements. It's like, it's just so, and by God, I believe it to be true. Okay? We don't know if this is possible. It's certainly possible in the ordinary laws of physics. It's good, then, to figure out how quantum mechanics would work on this. Deutsch proposed this theory. We proposed a separate theory, and we believe that Ben Schumacher and Charlie Bennett, had they actually managed to write the paper and work out the theory, would have arrived at the same theory. Okay? And it is different from Deutsch's theory. It has this nice feature that it can still be described in Hilbert space, but of course, because you have post-selection, you cannot uniquely assign a state to the system as it's moving along right here. We were also able to show that this was pretty tough because if you go read these Politzer and Hartle papers, they're about path integrals over Grassmannian variables. And it has been a long time since I did a path integral over Grassmannian variables. But you can show that they are equivalent to Politzer path integral method. At least for Politzer only does it for a single qubit. going backward in time. But they're equivalent for that in that case, so we think that they're actually equivalent generically to these path integral methods. And we performed an experiment, and by gum, we're going to probably do this experiment soon as well. And if you guys would like to do this experiment, we'll be happy to collaborate with you to figure out the right way to do it. So, thank you very much.
We're a bit late, but if somebody has a profound question.
Ramon has a group meeting right now, so maybe you should maybe you should go to your group meeting. Yeah, I happy to answer questions now and also later. Yes.
It's more a comment back to your original objection to.
Speak louder.
Yeah.
Right. So just to comment back on the paper, the Deutsche model against what Aronson and Waters.
Sorry, the IBM paper. Yeah.
Yes. I mean, should say it when the crowd is still here.
Yeah.
I think the difference here is just that we object to the model as trying to compute on a fixed input. And we think a computation algorithm should work on an arbitrary input that is decided on the spot.
Right. So in the paper, were you a co-author on the paper? Yeah. So in that paper, I actually say I'm still confused about the paper. So my understanding of it, now correct me if I'm wrong. So Aronson and Waters just said, hey, suppose we have an input and we can put an input into this. We have access to these closed time-like curves, and we are allowed to put in any input we want over here. And then we say, okay, what kind of problems we can solve? And the answer is they can solve problems in p-space. And your guys' paper, now is your chance to correct me if I'm wrong, says, well, hold it, you have to look at how you prepare this input, and that if you have these nonlinear systems, you're no longer allowed to think of things, a mixture as necessarily, when you apply something to a mixture, it's no longer the same as applying it to the individual components of the mixture and then seeing what happens to the individual components. So you say, well, you have to say, how do you prepare this input? And if it's entangled with some other state or something, then you can't necessarily prepare that input.
Would that change what you mean by the input, and therefore the fixed point changes as well? Therefore, the fixed point doesn't do anything for you, for each of the individual.
I agree with that, but having witnessed the Scott Aronson, Charlie Bennett steel cage fight, I have to say that my impression was, as I said, it was kind of a draw. So I don't think so the different assumptions are, Scott says we can prepare this input, and then we want this part of we have this part of the system, and we want to look at what happens. Whereas you guys say we look at the whole universe and we ask what it means to prepare an input then, and then if you just have a mixture of inputs coming in here, then you have to redo the calculation again. But that. I agree with that because I mean, the calculations in your paper are correct about that. But what I don't agree with, and I don't agree with this, okay? So I'll now come clean and say I actually don't agree with it rather than saying I don't know whether it's right. I don't agree that that's the correct way to talk about whether you can prepare an input or not. I don't think that Scott's way is wrong. I don't think that your way is wrong either. They're both different ways, and each is equally self-consistent. So I in fact don't think that your paper really refutes Scott's result. It's simply you choose to have a different definition of what it means to choose an input.
Maybe we can have a rematch of the Bennett and Aronson.
I got the pointy hockey stick here, man.
Try to go downstairs and try to find a cage.
Yeah, we can do it in the clean room. Oh no, that's not a bad. That's a bad idea.
This discussion here
Yeah.
offline after. Let's thank Seth again.
Thanks.